Hello calculus fans, and welcome to section 3.1 where we look at derivatives of polynomials and exponential functions. But we will be looking for the shortcuts this time. So your days of suffering through chapter 2 and the limit definition of a derivative are pretty much done. We'll do a few more of those, but mainly just to set something up, and we'll be using the so-called shortcuts for differentiation from pretty much this point forward. Start off with the derivative of a constant function. So C is just some number like 5, and we're looking at the derivative of a number, and it's always going to be 0, and we can think of that a couple of ways. We could just look at the graph. We could say look at the graph of y equals c. So if c is just some constant, like let's say y equals 5. Here's y equals 5. Well, what's the slope of this? Slope is 0, right? It's a horizontal line. And remember, we can interpret the derivative geometrically as the slope of the curve. So if you have a derivative of a constant, it's like saying what's the slope of this constant function, y equals 5. The slope is 0. So when you take the derivative of constant, you get 0. But you could say, well, I think I would rather use the limit definition. Well, that's fine too. You can use the definition. You could say f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x all over h. And if your function, so like if, let's say f of x equals c, then when you plug all this in, you're going to get f prime of x equals, well, f of x plus h, if f of x is just c, f of x plus h is still just going to be c minus c over h. Oh my gosh, look at this. I forgot. This is a limit. We need a limit here, right? And this is equal to the limit as h approaches 0. Well, c minus 0 is just 0 over h. 0 over h is just 0. So you have the limit as h approaches 0 of 0, which is just 0. So either way we go, the derivative of a constant is always just going to be 0. So let's consider the function f of x equals x. And maybe for this one we'll do the same thing. So let's just think of the graph. Okay, let's look at the graph. So if you have the graph of y equals x, all right, this is the one that we're all very familiar with. Graph of y equals x is just this right here. So what is the slope of that line, of the line y equals x? The slope is just 1, right? So it looks like if you have f of x, if f of x equals x, it looks like f prime of x would equal 1. But if you're not convinced by the graph, we can use the limit definition of a derivative. F prime of x equals the limit as h approaches 0. So if f of x is x, then f of x plus h would be x plus h minus x all over h. This, of course, is the limit as h approaches 0 of h over h, which is the limit as h approaches 0 of 1, and the limit of a constant is just a constant, so that's equal to 1. Okay, so basically, if f of x equals x, then f prime of x equals 1. So now I'm going to tell you the next two and see if you can see a pattern. So if y equals x squared, then y prime, and this is just other notation, right? I want to have you be familiar with other notation here. This just means the derivative of x squared with respect to x. So the derivative of x squared is 2x, and the derivative of x cubed is 3x squared. So looking at the pattern here, from x squared we get 2x, from x cubed we get 3x squared. If you had to make a prediction about x to the fourth, what would you think? I think you'd probably say 4x cubed. Okay, I mean, it looks like it's following some sort of pattern, right? It looks like this 2 ends up being a coefficient, 3 is a coefficient, so maybe the 4 is a coefficient. It looks like the powers drop by 1, or almost like this 2 comes down in front, and then the power drops by 1. 3 comes down, power drops by 1. So if these are true, then maybe 4 comes down and the x to the 4th becomes x cubed. But as you know, we do have one way to find out. So let's try this example 1. And we'll go back to the good old days of the limit definition of a derivative. And if you remember, we talked about how to do an expansion, which we're going to need with the limit definition of a derivative. So we'll talk about that. But let's just go ahead. Let's just find out if f of x is x to the 4th. Let's find out if we were right about our guess about f prime of x. So to do it, go back to the basics. Okay, f prime of x is the limit as h approaches 0 of f of x plus h, right? F of x plus h would be x plus h to the 4th power, because here's f of x. Then minus f of x, which would be x to the 4th, all over h. Then we can do the expansion here, which we talked about a shortcut for the expansion in 2.8. So let's see if you can remember it. Otherwise, binomial theorem, there are references typically in any calculus book. There's one in the Stewart calculus book also. But let's see if we can remember this one. So this ends up being the limit as h approaches 0. So we get x to the 4th plus, and then remember this 4 will come down. This is for the binomial expansion, so we get plus 4x cubed h to the 1, and then we go 3 times 4, which is 12, divided by 1, 2, gives us 6, plus 6x squared, h squared. So also, if you remember, the powers of the variables always add up to this 4. So we've got x to the 4th, h to the 0, then x cubed, h to the 1, x squared, h squared. Okay, and then we multiply again. 2 times 6 is 12, divided by 1, 2, 3. Gives us a 4. X goes down by 1, h goes up by 1. And then finally, we have x to the 1, so it's 1 times 4 is 4, divided by 1, 2, 3, 4 is 1. And x goes down by 1, and h goes up by 1. Okay, so that is the expansion of x plus h to the 4th right here. Again, if you don't remember how we did that, it's just a little trick to remember how to do binomial expansion. Not really important at all. You can look this up in tables. This is not something I would ever ask students of mine to memorize these. I just do them just sometimes just as a little extra. Okay, then we have to subtract this. So we go minus x to the 4th all over h. And just like before, we should be able to cancel everything that does not have an h. So those go. And then just looking, I'm just going to save a step here because we did this in 2.7 and 2.8. We can see that each term does have a factor of h. We can cancel all the h's. So if I cancel all the h's, that would give us the limit as h approaches 0, 4x cubed plus 6x squared h plus 4xh squared plus h squared, right? Because this h canceled and it canceled this, one of those, one of those, one of those. Now at this point we can take the limit. We don't have 0 over 0 anymore, and we can see that when we take the limit, all these terms with h's are going to become very unimportant. We can make these terms be as insignificant as we want by taking h closer and closer to 0, so that the limit then of this, when we take the limit, these terms will all go to 0, and we are left with 4x cubed, which was our guess. So what we ended up, the guess that you guys came up with was actually the power rule. So the power rule is a differentiation rule that we'll use all the time. And it basically says this. If n is any real number, then the derivative of x to the n with respect to x is just, you look at this formula, n comes down and becomes a multiplier, n times x to the n minus 1. And that is the power rule. Just a little note to save some confusion for later. Okay, n is any real number, but it's a real number. It's not a variable. So if this power had been a variable, we can't do this. The power rule is for power functions, so it's variable to a number, and the number can be any real number, but it cannot be a variable. Okay, so with this in mind, we've got some to try. Let's have you just first try let's have you try A, B, C, and D. Okay, so press pause and try A, B, C, and D, and then check back. Okay, you guys did try it, right? You're not just waiting for me, right? Math is not a spectator, well, I guess I can't say sport, not a spectator subject. You have to try. So make sure you try these and don't just wait for me. So this one says, so we're going to differentiate these functions. You got g of x equals x to the 8th. So this is perfect one for the power rule. It's a power function. So g prime of x, to find that, the 8 comes down, and we have x to the 8 minus 1, or 7th power. So g prime of x equals 8x to the 7th. Also notice the notation. We can't be sloppy here. I can't just say y prime. This is g of x. The function's g of x. Right? If your name is Bill, you don't want somebody to call you Marty, right? I mean, this is g of x, so this is g prime of x. All right, so the power rule here. Uh-oh, this one's going to be tough. 1,000? Are we ready for that one? This one would be quite a handful doing the limit definition of a derivative, but we don't need to. We have the power rule, so it's really easy. So if y equals x to the 1,000th, and differentiate, we get y prime equals 1,000x to the 1,000 minus 1, which would be x to the 999. If anybody would like to verify that with a limit definition of a derivative, go ahead and start, and 3 years from now you should be able to verify this. That would be a lot of work. Don't do it. All right, part C. Well, the power rule works for any real number, including rational expressions like 4/3. So we do the same thing. Again, let's pay attention to what we're doing. We're differentiating. If this is y, I can't say f prime of x, right? If this is y, I want y prime equals, this one comes down, so you get 4/3 x. Let me write that first. 4/3 x. And now I'm going to have to the 4/3 minus 1, which is like saying 4/3 minus 3/3, right? 4/3 minus 3/3 would just be 1/3. So I can put a 1/3 here. Okay, everybody good so far? All right, then we have this one. This is similar, right? But it's 3/4 now. Again, details are going to matter. When you are all done with college, out there being underworked and overpaid, making the big bucks, you make those big bucks because you're going to be the person who pays attention to details. So you would never say f prime of x here, and you wouldn't do this. Okay, here's something that students say sometimes. Equals 3/4 x, and then they say, okay, so 3/4 minus 1. So 3/4 minus 4/4 is negative 1/4, right? So we just get a negative 1/4. Okay, look at that. Tell me, does that look right? When you look at this, you should have to look away. You shouldn't even be able to look at that. It should hurt to see. Is this true? Can I just put equal signs wherever I want? Not really, right? If this is y equals this, y does not also equal this. This is y prime. I know. Kind of picky, but remember, you're in a STEM field. People expect you to notice things and to be picky. right? So y is equal to x to the 3/4. So to differentiate, we do the power rule. 3/4 times x to the 3/4 minus 1, or the 3/4 minus 4/4, which will give you to the negative 1/4. Okay, then they're going to try to be a little tricky here with part E. Well, we only have one rule so far. We just have the power rule. So if something doesn't fit the power rule, we can see if we can make it fit and then use it. Otherwise, we're going to need more tools. So with this one, how could we rewrite this so that we could use the power rule? Probably, you remember the good old days in algebra class when you had this rules of exponents that said x to the negative n is 1 over x to the n, right? So you can move these around as long as you switch the signs. So this one, isn't 1 over x just the same as saying x to the negative 1? Right? 1 over x equals x to the negative 1. And you can verify it right here, right? But here we can use the power rule. Here we can't, but here we can. So now we can find the derivative. Okay, I'm going to do something terrible just so you can see and catch the mistake. So minus 1x to the minus 1 is minus 2. Or maybe negative x to the minus 2, but something terrible is happening again. Can I just put equal signs wherever I want? No. This is not f of x, this is f prime of x, right? And you could also write this differently. So this is fine like this, but sometimes you look in the back of the book maybe and they look different. Well, you could just use this rule again, right? So I mean, this is fine, this answer is good. But you could also say, well, this is equal to negative 1 over x to the positive 2, right? So you could do that too. Either way is fine. And then what about this one? The derivative of the square root of x. Again, we need to use the power rule. Who remembers how we can write the square root of x using rational exponents instead of a radical? Raise your hand. Okay, I think I see some hands being raised out there. Okay, isn't this just the same as taking the derivative of x to the 1/2 power? 1/2 power. So now we can use the power rule. Remember, because the square root of x is just x to the 1/2. So if you ask your calculator, is the square root of 25? Or you say 25 raised to the 0.5, you should get the same answer. So with this one, we can now use the power rule. So the 1/2 can come out. So then, in this case, I can just say equals, right? Because this question is, what's the derivative of this, right? What's the derivative of this? So I can just say equals, the derivative equals 1/2 x to the minus 1/2, right? Because you have to go 1/2 x to the 1/2 minus 1. 1/2 minus 1 is minus 1/2. And this is fine just like this, but I'm going to show you how you'll usually see it. Normally, you'll see it like this. People will write it like 1/2 times 1 over x to the 1/2. Once again, using our rule here. But then usually x to the 1/2, at least in our textbook, in the Stewart textbook, would typically be written this way. I have 1 divided by 2 times the square root of x. Okay, so this is fine. These are all right. But this is usually the one you'll see in the back of the book. When there's an x to the negative 1/2, they'll typically put it in the denominator and they'll use a radical for it, okay? All the same. Okay, oh my gosh, look at that. There's been an addition magically appearing on the handout. Is it on yours too? The font looks a little different. I think this is a Kurt font. But let's try this one. Y equals the 5th root of x squared. What do we do with this? Well, we want to get rid of these radicals. So this is the 5th root of x squared. So we could say, I believe this is the same as x squared to the 1/5, right? Just like the square root of x is x to the 1/2. the fifth root of x is x to the 1/5. And then here we got a rule from algebra that says that for exponents like this, we multiply. So this is really equal to x to the 2/5. And now we are good to go. From here we can say, okay, if that's y, then y prime equals, we've got the power rule, so it's going to be 2/5 x to the 2/5 minus 1, or 2/5 minus 5/5, which is negative 3/5. So, all right. Hopefully those went pretty good. The power rule is one we'll use a lot when we're taking derivatives, and it's very fast and easy to use. So the next couple of rules here, we're going to mention them just so you're aware of them, but these are something you'll do automatic. Like once you see them, you'll automatically doing these without even thinking. Okay, so the constant multiple rule just says if c is a constant and we've got this differentiable function f of x, then the derivative here, the derivative of a constant times the function, we can move this constant out in front of differentiation and then take the derivative of the function. And so with this other notation, we use the prime to mean derivative. This c just goes along for the ride. So the derivative, you take the derivative of the function and the c just goes along for the ride. It's unchanged. C times the function, take the derivative, you get c times the derivative of the function. Okay, so what I'll do first is just walk through this the slow way, and then I'll just show you the way we typically would do it. So going step by step, we would say, okay, this 4 can come out front, and then we can take the derivative of the x cubed, right? So that's what the rule says. So then it's 4 times the derivative of x cubed is 3x squared, and then we can multiply and get 12x squared. Okay, so that's what the rule says we can do, but you don't really want to go through all this right here. So what you really will do, now that we know that we can do this, what you do here is when you take the derivative, you just go 3 times 4 is 12, x to the 3 minus 1, which is 2. So you'll sort of go right from here to here in one step. 3 times 4 is 12, x squared, right? These are just to be aware that it works. So there's a constant multiple rule that says we can do that. Same with this one. So this one, we've got this -1 out front. We could just say, all right, I'm going to think of this as -1 times the derivative of x. And the derivative of x is just 1, so this is -1 times 1, which is just -1. Okay, so you can sort of skip all this just by saying, well, the derivative of this, this is just like -1 times x. I know the derivative of x is 1, so the -1 just goes along for the ride. Okay, so we don't have to actually go through all these steps. This just says we're able to differentiate this way. The sum and difference rule is very similar. So I'll mention this and we'll kind of automatically do it without thinking. But it basically just says that if you read it as a sum, the derivative of the sum is the sum of the derivatives. And the derivative of a difference is the difference of the derivative. So we can basically do these individually. We don't have to combine these first and then take the derivative. We can just do them one at a time. So if you have something like this long expression, when I look for y prime, so if I go to take the derivative here, I can just do these one at a time. Derivative of that, right? Just one at a time. Okay, so here's where you come in. Don't wait for me. Press pause and try this one, and then check back. Okay, hopefully you guys are pressing pause. You are, right? If not, press pause and check back. All right, so with this one, this is just the power rule of 7 times 3 is 21, x to the 6. So you get 21x to the 6. Now this one, this 6 comes down and it gets multiplied by 1/3, right? So you get 6 times 1/3, which is like 6/3, which is 2. Also, there's a negative. So you get -2. Everybody okay with that? 6 times 1/3, right? 6 times 1/3 is 2. X to the 6 minus 1, which is 5. Okay, and then we've got this square root of 2. Remember, the power rule works for any real number. So we multiply here, we get 10 times the square root of 2. It's a positive, right? Because there's a plus sign. Then x, what's the square root of 2 minus 1? Don't say the square root of 1. It's not that. It is just the square root of 2 minus 1, right? That's all we can say there. And then over here, we've got minus 4. We've got a minus here, so this comes down, so we get negative 4. Well, minus minus is a plus, right? So we get plus x. Here's where we have to be careful. It's minus 4 minus 1, right? Minus 4 minus 1 is minus 5. And then the derivative of 6, well, 6 is a constant. The derivative of any constant is 0, so we don't really need to add that on there. You can if you want to. But that's it. So this is y prime, and we just broke these up into pieces and took the individual derivatives. Uh-oh, something terrible happened this time, not on purpose. Look at this. You guys see something here? Were you screaming at the computer screen? I hope you were, because what did I forget? When I multiply down here, I get 4. I think I may have said it, but I sure did forget to write it. Okay, we need a 4 there, right? 4x to the negative 5. Okay, very good. So those of you who are screaming at the computer screen, thank you. I must have heard it somehow. And I said, I better look at that last one. So 4x to the negative 5. Okay, here comes example 6. This one, when you look at it, this doesn't look like the power rule at all. But can we fix it? Remember, we've got one rule right now. We just got the power rule. And it's a really sweet rule, but it's only one. Later, we're going to find the product rule, where we could use this product rule on this. But sometimes the power rule is still easier. We just have to do a little bit of algebra first. So they want us to find h prime of x. And the power rule is not going to work here. So what we have to do is a little bit of algebra, right? So we'll just have to multiply these together. Remember the good old-fashioned FOIL method from the good days in algebra class? First times first, outside times outside, inside times inside, and last times last. So you go first times first, outside times outside, inside times inside, last times last. FOIL method is just an acronym to make us remember to distribute properly. So if we go over here, I'm going to say h of x equals, right? So I'm going to multiply here, so you get 2x squared. Outside times outside gives us plus 3x. Inside times inside minus 4x, and last times last minus 6. Now this, you're going to want to just clean this up. Generally, before you take the derivative, it's going to be easier if we just always clean things up. Add like terms, simplify. So this is 2x squared minus x minus 6. And here, from here, we're all set, right? From here, we can use a power rule. Okay. Let's do a what if. What if you're on a date? Things are going great. This date is perfect. After the date, you say, hey, want to work on some calculus homework? And your date's like, I sure would. You know how it is. So you're working on your calculus homework, and let's say you're working on this problem, and your date, which seems wonderful so far, your date says, here's my answer. Want to go on another date someday? What are you going to say? You're going to say, absolutely not. That is not a good answer, right? That's a giant red flag in a relationship. That can't be right, because what is this? Look at that sloppiness. Are these the same, really? No, we can't put equal signs wherever we want. We have to write h prime of x. Okay, as you know, I'm trying to prepare you for your future, not just in math, but also your dating future. So that's a red flag. We need dates. We're going to put h prime of x where it belongs. Okay, everybody good with that one? Okay, let's move on. Example 7, I know what you're thinking. That is a good-looking problem. It is. It's a bit of a handful. It's definitely not ready for the power rule. yet, right? Well, this one's going to take a little bit of tweaking, but it can be done. Because what we can do is break this up, right? So if you had this kind of question, let's say 5 over 3 plus x over 3, we know that since we have a common denominator, we can keep that common denominator and just add the numerator, right? 5 plus x. Which means we could go backward also. We could start here and go here. So that's what we'll do over here. We're going to break this thing up. So f of x is really equal to the square root of x over x squared plus x over x squared. And now we're going to use a rule from algebra. A to the m over a to the n, isn't that equal to a to the m minus n, right? Just remember that this square root is really 1/2, right? So what we could do, this is really x to the 1/2. So we could do this. We could say x to the 1/2 minus x squared. That's 1/2 minus 2. That's x to the minus 3/2. Plus, now remember this x is really x to the 1, so it becomes x to the minus 1. Right, and now we're ready to go. Now we can use the power rule. So now we say f prime of x equals negative 3/2 x to the minus 3/2 minus 2/2 is minus 5/2. And then we have this minus 1 that comes down, so we get minus x to the minus 1, which is minus 2. Example 8 asks us to find the points on the curve y equals x to the 4th minus 6x squared plus 4 where the tangent line is horizontal. Well, we have to make a little note here. Tangent line is horizontal is an important idea for us. The tangent line is horizontal. A horizontal line has a slope of 0, right? So it's basically saying find the points on the curve where the tangent line has a slope of 0. Well, if it has a slope of 0, doesn't that mean it has a derivative of 0? Right? So it's sort of like saying find where the derivative of this function is 0. Right? So the other note here is horizontal tangents occur where the derivative, or in other words, the slope, geometrically, right, the slope is 0. It ends up being an important concept because a lot of times that's where the maximum or the minimum will occur of some sort of function you're trying to optimize. So we're going to be looking for these areas a lot. So for this one, I'm going to sketch a curve. I'm going to sketch a graph of this curve. Okay, it looks something like this. This one is actually example 6 in the book. And it's just such a good example. I just like to use this one. So we're looking for, if you look at the slopes here, there'll be some tangent slopes like here, right, where the tangents are 0. All these have slopes of 0. So there'll be some points here we're looking for. These points where the slope is 0, where the tangent line has a slope of 0, the tangent line is horizontal. It means where the derivative is 0. So to see how that works, let's find the derivative of y. So y prime, just using the power rule here, it's going to be 4x cubed minus 12x, right? So it's 4x cubed minus 12x. And there is no, the derivative of 4 is 0, so that's it. It's just these two terms. And we need to see where is this 0. So what we do is we take that derivative and we set it equal to 0. So we have a cubic, which typically would be a nightmare to try to solve, but in this case, it's not at all because we can factor out a 4x out of here and get x squared minus 3. Right, so now we can use the zero product property, which basically just says if I'm multiplying two things together, this thing, and I get a 0, the only way that can happen is if either this one or both are 0. Right, so it could be that 4x equals 0, or it could be that x squared minus 3 equals 0. If 4x equals 0, that just means x equals 0. right? You could divide each side by 4. Or over here, if x squared minus 3 equals 0, it means x squared equals 3. And that means x equals plus or minus the square root of 3, right? Because if you have x squared equals 3 and you want x, we have to take the square root of x squared. But remember, when we do that, when we take the square root of x squared, we're going to get this plus minus in there. So we take the square root of this side too. So you get plus or minus, right? Because we know that if I take negative square root of 3 and squared, I still get 3, right? Same with a positive. So that means the corresponding points then, because they wanted the points, right? They want an x and a y coordinate. So the points that we have, the corresponding points, the points that correspond to these x coordinates are going to be 0 something, right? The square root of 3 something, and a negative square root of 3 something. The way we find the somethings is, well, we have to take these x coordinates and plug it back in here to find y, right? These are points. They have x and y coordinates, right? Points, an x and a y coordinate. So we've got the x coordinates right here. These are 3 x coordinates right here. Here they are. So to find the y coordinates, we just plug in the x's here. So for 0, if x is 0, y is 4. So then to find the other ones, let's take a look at the square root of 3. So y equals x to the 4th minus 6x squared plus 4. And I want to figure out what happens when x is the square root of 3. So if I plug in the square root of 3 here, well, if you look at this first term, the square root of 3 to the 4th power, the square root of 3, really, isn't that just 3 to the 1/2 to the 4th power? So that's going to be really, when you multiply here, don't you get 4 times 1/2, which is 4 halves, or 2? So that's really 3 squared. 3 squared is just 9. Over here, we've got the square root of a square, so these are really going to cancel out, right? So if you take the square root of 3 and square it, you just get 3. So you get negative 6 times 3, which gives us minus 18 and then plus 4. So minus 18 and then plus 4. So 9 minus 18 is negative 9 plus 4 makes negative 5. So this y coordinate here is negative 5. And if you look carefully, you can see that if I were to replace the square root of 3 with a negative square root of 3, nothing changes because these are even powers. So if there's a negative here, when I raise it to the 4th power, it will be a positive also. And same thing over here. If I put a negative here and square it, I'm still going to get a positive. Right? So we get the same thing. So for the other y coordinate is also negative 5. And then you can see the points up here. This point here is 0, 4. This point here is the square root of 3, negative 5. This point right here is minus the square root of 3, negative 5. You can also see that my hand sketch is not exactly scaled properly, but not too bad. Now, if you remember these kind of problems from 2.7 and 2.8, where they give you an equation of motion and ask you to find the velocity and acceleration, these were a lot of work because we had to use the limit definition of a derivative. But now we don't. Now we can just use the power rule. So life is going to be much better. So to find the velocity, remember we've got an equation of motion. So we've got a position function. So if you remember, if we've got a position function like s of t, this is position, and we take the derivative of this with respect to t, we'll get the velocity, which is the derivative of position, right? So you get velocity. Then if we take the derivative of this with respect to t, the derivative of velocity with respect to t, we get acceleration, which is the derivative of velocity or the second derivative of position, and that would be acceleration. So with that in mind, let's find the velocity of this one. So the velocity, or in other words, v of t, equals s prime of t, and that would be, just using the power rule, 4t cubed minus 6t squared plus 2t minus 1. So remember to press pause occasionally and try these out. You know, don't just wait for me to go through them. You want to make sure you get practice also. So that's the velocity. If we wanted to find the acceleration, at time t, well, that's going to be the derivative squared, right? Or the second derivative of position. So now we just take the derivative of this function with the power rule, and that is going to be 12t squared minus 12t plus 2. So once we have these formulas, then we can answer any question they ask, like find the acceleration after 1 second. We've got the acceleration formula here. Now, just to be careful with the units, it tells us that the position is in meters, right? And t is in seconds. So we plug in t seconds, it'll give us the position. Remember, this is going to be a straight line motion. So after, like initially, when time is 0, position is also 0, right? Because these will all be 0. So to get the velocity is the change in position with respect to time. So the velocity, the units of velocity are going to be meters per second, right? Because position would just be in, the equation of motion would give the position, which would be in meters. So velocity would be change in position with respect to change in time, meters per second. Acceleration is going to be the change in velocity with respect to time, which is meters per second, or what we normally write is just meters per second squared. Okay, so they didn't ask us for this here, but I just want us to keep in mind units are important. So the acceleration after 1 second, we got the acceleration formula. Acceleration at time t is 12t squared minus 12t plus 2. So after 1 second, it's going to be 12 minus 12 plus 2, or in other words, 2 meters per second squared. So, calculus fans, we now are all set with polynomials. We know how to take derivatives of polynomials. So we are ready to move on to exponential functions, which are a little bit more challenging. So let's say we start off with f of x equals a to the x. And we don't know what to do. So we just want to go to back to the basics, right? So let's do the limit definition of a derivative and see what happens. So f prime of x is going to be the limit as h approaches 0 of f of x plus h minus f of x all over h, right? So that's the limit definition of a derivative. So if we fill in the blanks here, we have the limit as h approaches 0. So our function is a to the x. So f of x plus h is just going to be a to the x plus h minus f of x, which is just a to the x all over h. And what had happened in the past is we got a whole bunch of things to cancel, right? Anything that didn't have an h would cancel. But we're not going to be so lucky in this case. So what we could do is factor out an a to the x, and that would give us a to the h minus 1 over h. And just to make sure you see this, if this distributes through, I get a to the x times a to the h. And that's when we add these, right? So if you have something like an old formula from algebra, if we had x squared times x cubed, we have x to the 5th. We add those, right? This is saying I've got 2 of these x's lined up multiplied together, then multiplying that by another 3 of them lined up multiplied together, so that's 5 altogether. So that's why we can do that. And then we can actually move this a to the x out front because it has nothing to do with the limit as h approaches 0. So this can come out front. So that would give us f prime of x equals a to the x times the limit as h approaches 0 of a to the h minus 1 all over h. But in order for this limit to exist, if this limit's going to exist, we've got this out front here, this is going to have to be equal to a number L, right? For this limit to exist, this thing is going to have to be a number L. So just say a number. Remember we talked about limits before? And we'd say the limit to exist, it has to be some real number L. Same thing here. So if we take the derivative of a to the x, it sort of comes back. It's a to the x times some number L. So it'll be some multiple of itself. So I take the derivative of a to the x, I get some multiple of a to the x. Now looking at this, we can already see that if I take the limit, we're going to have a problem here because as h approaches 0, I get a to the 0, which is 1. So I get 1 minus 1, which is 0 over 0. So this is a 0 over 0. It's an indeterminate form of 0 over 0. So it's a problem. And we also know that if this limit exists, we need to be able to figure out what this is to find the derivative of a to the x. So to make what I just said official, I'm going to write it down here. So I've got this note. The rate of change, or the derivative of any exponential function, is proportional to the function itself. Because look at this, f of x is a to the x, f prime of x is a to the x times some number. Like if this derivative exists, if the limit exists, this has to be a number. So it's just some number, which means this function, the derivative of this function is just proportional to the original function. Okay, and also there's another note we need, another note to mention. Just notice that if we had f prime of 0, and if we went through f prime of 0 and we went back to this, right, we did this, we're taking the derivative at 0, we would get the limit as h approaches 0, f of 0 plus h minus f of 0 all over h. So for our function, we get the limit as h approaches 0 of a to the 0 plus h minus a to the 0 all over h. And this is equal to the limit as h approaches 0 of a to the h minus 1 all over h. Right, because a to the 0 plus h is just 0 plus h is just h, and a to the 0 is just 1. And so if you notice, we got this same thing back again. Here and here. So when we take the derivative of this function at 0, we get this multiplier again. So we know this. Based on this, we know this much. We can say that we know f prime of x is equal to a to the x times f prime of 0. Right, we know this for the derivative, or for the function we've got. If f of x equals a to the x, then we know that f prime of x, the derivative, is the original function times the derivative of the function at 0. So what we're looking for, we want to find, is there a base a such that f prime of 0 equals 1? Because that would mean you take the derivative of a to the x, you just get a to the x, right, if this is 1. So that is the question. We want to see, is there a base a such that f prime of 0 equals 1. So we take the derivative of that base at 0 and we get 1, because if this were just 1, then f of x equals a to the x, and f prime of x is also a to the x, so the derivative didn't change the function. So let's see if we can find that base a. So as we search for this base, I'm going to not just blindly search, I'm going to use what people who have come before us have found. So if you look around 2 or 3, so in other words, let's say f of x is 2 to the x. And I'm looking for this. I want to see, is there a base a such that the derivative at 0 is 1? So if the base a is 2, so if a is 2, then here would be the function. The derivative of this function at 0 would look like this, right? From the work that we did above. Or maybe a equals 3. So in other words, the function is f of x equals 3 to the x. In that case, f prime of 0 would be this. So what we're going to do now is just see, we don't really know how to take this limit yet. So let's see if h approaches 0, what it looks like this is heading towards. And with this, we'll go back to what we did at the initial, when we initially started the calculus and we didn't have much to work with. And we're making educated guesses with the calculator. So I'm going to just do this for a couple of these. Okay, so what I'm going to do, I just put this in the calculator under y1. So I put y1 equals, of course I used x, 2 to the x minus 1 in parentheses divided by x. And then in y2, I just had 3 to the x minus 1 in parentheses divided by x. And then I'm going to plug in these various values of x. So I'm going to have 0.1, 0.01, 0.001, 0.0001. And basically, I just want to see, we're just really hoping that one of these looks like it's going to be 1. And if you plug these values in, so, I mean, it's easier to use a table. You could just plug this in like this, right? Just plug this in and see what you get. I'll save the time. This is just basic arithmetic on your calculator, but you get something like this. So these values for when f of x equals 2 to the x, and you start plugging these in, and it's just not really going to 1. And then with 3, you do the same thing. We get something that's also not really going to 1. Okay, so it's like this one here, this limit looks like it's about equal to 0.69. Let me rewrite that, 0.69. And this one, it looks like it's about equal to 1.10. So what we want, we really want some number that's probably between 2 and 3 such that this is exactly 1. Right, that's what we're looking for. We want the derivative at 0 to be 1. So we want some number that when we do this, these numbers will be approaching 1. So sometimes in math, if you really want a number and you can't find it, you define a number. So this is what we're going to do. We are going to define the number e. The number e is a very interesting number. It's a transcendental number like pi. It will come up in all over the place, really in unusual places. We're going to define it differently later, but it turns out these definitions are equivalent. So we're going to say this. We're going to say e is the number. E is a number such that the limit as h approaches 0 of e to the h minus 1 over h equals exactly 1. It's a strange thing. I know it seems strange to make up a number that works, but you'll see other definitions also. In fact, let me just mention these. Okay, e. So there are these alternate definitions that are equivalent. Probably the first time e came up was, believe it or not, in finance with these compound interest formulas. So you've probably seen the compound interest formula. The amount equals the principal times 1 plus r over n raised to the nt, and rate is the interest rate as a decimal in here, and n is the number of compounding periods per year, and t is the number of years. And then you'll see later that as n approaches infinity, as n gets bigger and bigger and bigger, so we have more and more compounding periods per year, that sort of sends this number towards 1 and this number towards infinity. So you have 1 to the infinity. And what you get then is this other formula, a equals pe to the rt. Yes, the very e we're looking at. So from here, you can define e, and we'll do this later in calculus. This will come up later. You can define it to be the limit as, we'll use n here, I guess, as n approaches infinity of 1 plus 1 over n to the n. And also, you can define it to be the limit, typically is done with x, but you could use n here too, it doesn't matter. So x approaches 0 of 1 plus x to the 1 over x. So here are 3 definitions of e, this whole sentence, and then these two also. But this kind of corresponds, of course, to what we're doing right now, because we're looking for a base such that when I take the derivative of that base to the x, I just get that base to the x, because the derivative at 0 is 1. So we define this to be the case. And then, because of that, we can say this. We can say that if f of x equals e to the x, f prime of x also equals e to the x. So in other words, we can say the derivative of e to the x is e to the x, which is our second rule. So now we have the power rule and we have this. This is a little limiting. I mean, we would have liked to have found, like, really what we wanted is we wanted this. We wanted to know what is the derivative of a to the x, right? Well, for any general base a, we're going to have to wait on this one. For now, this is the best we can do. We can say the derivative of e to the x is e to the x. This will come soon. We're just not quite ready for it yet. So this is the derivative of the natural, it's called the natural exponential function. And when you see that, it just means base e. It's a base e. We'll use this a lot. It's related to natural logs, which we will use quite a bit also. But geometrically, this has a consequence geometrically. It's kind of interesting. So let me draw a picture of this one. Okay, I added a little bit here. But here's what we've got. So you know that the derivative of e to the x is equal to e to the x. So if I draw the graph of y equals e to the x. So what this means is the slope of a tangent line to this curve. The slope of a tangent line to this curve is equal to the y-coordinate at that point. So here's y equals e to the x. The slope of the tangent to the curve is going to be equal to the y-coordinate. These are going to be the same. So the slope is 1, the y-coordinate is 1 because of this. Here's the y-coordinate. And we know that e to the x is equal to its own derivative, which means it's the slope. So if I were to find the slope of this curve at this particular point, the slope right there, that slope is equal to the y-coordinate of the point at that point. All right, so it's just kind of an interesting thing that happens when you take the derivative of e to the x and it's still e to the x. So the main takeaway we need to know is that the derivative of e to the x is e to the x. And we'll see e to the x quite a bit in our calculus careers. But basically the little geometric takeaway is that the slope of a tangent line to the curve y equals e to the x is equal to the y-coordinate at that point. Okay, so that should give you all you need to get started on section 3.1. So from here, you know what to do. You have to do the homework, right? It's the only way to learn it. Work on the homework. And if any questions come up, just let me know. And I will talk to all of you very soon.